Welcome to the NYU Tatlin School of Engineering. Those of you who know me or who have been to any of the seminars know that I'm fond of a quote attributed to Albert Einstein. The important thing is not to stop questioning. Curiosity has its own reason for existing. To that, I would like to add one more line that resonates with me. It's from a 1935 issue of the Saturday Evening Post in an article by Eleanor Roosevelt, who wrote, "I think at the child's birth, if a mother could ask a fairy godmother to endow it with the most useful gift, that gift should be curiosity." Whether or not you believe in fairy godmothers, you're here today because you are curious people. So thank you for both your presence and your curiosity. Thank you as well to Tandon Executive Dean Juan de Pablo, who is also serving as NYU first Executive VP for Global Science and Technology, and Senior Vice Dean Ray Odile for their support, and to my own Department of Electrical and Computer Engineering for hosting the seminar series in Modern Artificial Intelligence. I launched this series 7 years ago, and it has been among the greatest honors of my career to see it evolve into a significant event in the AI world and a vehicle for unifying scientific communities around the influential research ideas of today that can have a major impact tomorrow. It's thus with great pleasure that I introduce today's speaker, who truly exemplifies intellectual curiosity and impactful research. Elad Hazan is a professor of computer science at Princeton University, as well as the co-founder and director of Google AI Princeton. His work focuses on the design and analysis of algorithms for basic problems in machine learning and optimization. Among his contributions are the co-invention of the ADA-GRAD algorithm for deep learning, the first sublinear time algorithms for convex optimization, and online non-stochastic control theory. He is the recipient of the Bell Labs Prize, the IBM Goldberg Best Paper Award twice, a European Research Council grant, a Marie Curie Fellowship, and 2 Google Research Awards. He served on the steering committee of the Association for Computational Learning and was program chair for the Conference on Learning Theory in 2015. I could go on listing his many impressive credentials and accomplishments, but I know we are all eager to hear his presentation, which is intriguingly titled Spectral Transformers. So without further ado, let's warmly welcome Elad Hazan.
Thank you, Anna, so much for inviting me, and such a beautiful room and place to be giving a talk. And it's really impressive. You got all this community together to study AI, so it's a great pleasure. Can you hear me well at the back? Is this okay? The speaker is fine? Okay. So my name is Elad Hazan. I'm from Princeton, and I'll talk today about a new architecture for sequence prediction, which is motivated by theoretical developments in control. And I like to take questions. So if you have any questions during the talk, please feel free to ask. This is a joint work with many people, both at Google AI and Princeton University, and they're listed here. The first of which are Naman, Shini, and Daniel, and then more recent work with Annie, Evan, Isabel, and Windsor. And the motivation for the topic of today are transformers, which, as we know, have revolutionized the way we do deep learning and the way we do sequence prediction, especially for large language models. So more precisely, we're motivated by a computational issue with transformers. And this computational issue has to do with one block, which is called self-attention, where we compute the correlation between 2 words, any 2 words in the attention context that we have. And naively, this will take quadratic time. So when we have a context length, now we're talking about in Google about context of a million, that is large, right? So the million squared is a large number, and it's very time consuming, and we really want to improve the running time. Now, if you're familiar, if you have been doing work, you've maybe coded up a large language model or played around with it, pre-training, fine-tuning, you know what I'm talking about. So I also like to run it by ChatGPT and ask him, if you didn't completely get what I'm saying, and you can do that on your own. So it really does a great job of explaining what is the quadratic bottleneck in compute for the transformer architecture. I'm not going to read all that, but just so it's nice that it's aware of this issue. And this issue has not gone unnoticed in the research community. And in fact, it gave rise to a lot of work going back to a previous architecture of recurrent neural networks. These were predated transformers by a lot, have a rich history going back to at least a few decades. And basically, recurrent neural networks they have been reformulated something in a control theoretic language as state space models. And there are much smaller networks that have backward edges and therefore are suitable for sequence prediction. Although traditionally, so the literature from a few decades ago suffered from various issues. So we had vanishing gradients, exploding gradients. This was very hard to train. That's why people moved to transformers. But what happened a few years ago, this started from Chris Ray group at Stanford, is that there is a resurgence of study in this particular architecture, and people have, using all sorts of tricks, been able to train them to large scale models and achieve state-of-the-art performance. They have many advantages, mostly what the motivation is that they're faster. So you have a neural network that's of constant size. It's independent of the sequence that you're feeding it, right? So therefore, to generate a new token, you're not spending time proportional to the history length. You're spending time only proportional to how many ever nodes and weights you have the network. Can you all hear me in the back? Is that fine? Okay. So they have a computational advantage, and people have been able to train them recently pretty well to large-scale corpuses, but they don't work well with efficient, so they are not able to memorize long context very well. There is a memory issue for these machines, and people who have trained them to large-scale large language models know that they have a hard time remembering something that happened a long time ago, because they don't have that, right? All they have is the internal weights and the internal state. So long context is a problem for these machines. So to summarize, we have transformers, they have a computational issue, state-based models overcome that issue, but they have a memory bottleneck. So the question for this talk is, can we have an architecture that is efficient and provable and also allows for long context, so long memory? Remember things that happened long ago in terms of prediction power. So this is the motivating question. The outline I want to go over with is start with some talk about dynamical systems and linear dynamical systems, some new technique in that domain, and how it gives rise to this new neural architecture that I want to advocate, has long context capabilities, and is also efficient in terms of generation and training. So to a topic that seems a bit unrelated, dynamical systems. Actually, it's very related. When we do sequence prediction, we can think of our whole brain as a dynamical system. It has a state, it observes the previous tokens and predicts the outcome. And that, of course, affects the world and comes back as feedback to the next token. Study of dynamical systems is extremely old, much older than deep learning. Here are two of my favorite dynamical systems that to illustrate. One of them is the inverted pendulum. So here we have a ball on kind of a long stick, and the goal is to balance it. For example, if I have this thing here, the goal is maybe to move my hand in such a way that this stays upright. This is a dynamical system. The other here is a device that worked in my lab during COVID. It's a medical ventilator. Again, the goal is you have a sedated patient. You want to insert air into the lungs of the patient in such a way to keep them breathing healthily, to track a healthy breathing waveform. What I like about this dynamical system, and this also, so it has a very low dimensional representation. We have a one-dimensional input and output. You can see the pressure in the lung. We have the pressure that we're inserting into the airways of the patient. But what goes on behind the scenes is very complicated, right? We have the whole lung-patient interaction and maybe some obstructions and so on. So all of this goes into the high dimensionality of the dynamics, and we don't see it in terms of the observation or the actual input to the system. Here's the mathematical model that I want to be working with. It's called the linear dynamical system. The two dynamical systems that I talked about are obviously nonlinear, but this is a good approximation. It was advocated by Lyapunov that linearization makes sense, and it's also easy to analyze and gives rise to efficient algorithms. So let me go over the notation. The observation, so we have an input time series U and an output time series Y. For example, in the ventilation, it's how much air we put into the airways of the patient. and then y is the pressure that we measure. So these can be scalars. But what goes on inside of the system can be very high dimensional, and that is represented by a hidden state called x. So x is manipulated by the dynamics function here, by this equation, according to a linear function, so given by the matrix A. This is called the system, A and B and C and D, the matrices. So this hidden state is manipulated according to this equation, according to the previous state and the new input to the system. So eta and zeta, these are noise terms, potentially. And the important thing to understand is that the state can be very high dimensional. So even though I see low dimensional representation, there could be something very complicated going on behind the scenes. And that gives the power to the model to represent a lot of advanced systems. The way I would model a large language model is, again, so the input and the output would be the same series, just one token. Here, I will look at one token ahead of what I'm predicting. And this would affect the next state and so on. So this can also be a sequence of tokens if I'm talking about large language models. Have people seen this model before? Kind of a basic model. It's not very well studied in computer science, but in engineering, it's very well studied, even in undergrad courses. Okay. Questions? Okay, so here is a more recent way to study linear dynamical systems. It's one of my favorite ways to analyze learning. It's called online learning. In this setting, we observe an input. We try to predict the output using the same notation as in the previous slide. So we see the U, we predict a Y. It's based on all the previous inputs that we have seen. And then we suffer a loss, let's say the mean square error. For example, I could have taken coarse entropy if it's tokens or whatever other loss functions I want. And this is sequential in nature. How do we measure performance? It is standard in online learning to measure performance relative to a benchmark. And this is useful because many times I don't want to make an assumption about the underlying sequence that I'm observing. It's very hard to model the actual dynamics, whether it is a sequence of language tokens or other measurements. So a standard way to measure performance is by regret, which would be, for example, the mean square error of our algorithm as compared to the mean square error of the best linear dynamical system in hindsight that matches the data. So this is a meaningful metric of performance, even if the data didn't come from a linear dynamical system, because I'm only measuring performance relative to some benchmark class. Yeah.
Suppose you don't have the previous LDS.
This doesn't assume that I know what the best LDS is.
Okay.
It just compares to it. And many times I can say something in comparison, even if I don't know what it is. That's actually what I'm going to show.
Okay.
Yeah, good question. Any other questions so far? Okay, so let's try to do this, to minimize regret in this setting of online learning of a linear dynamical system, if we understand the setting. Well, one thing which we can try to do, and I guess was advocated by Larry here, I can try to identify the system. So maybe I can try to identify the matrices A, B, and C that govern the system, how it evolves, and then plug them in, because I know that the output should be, if indeed this came from a linear dynamical system, the output would look like these matrices with repeated powers, because I have the state, it's multiplied by my transition matrix, and what is this state? I can kind of unfold it one back. So again, I apply the transition matrix and so on. The output would look like this kind of polynomial function of the past inputs. Maybe I should go back to the equation just to remind you how this looked like. Oops. Yeah, so, right, what is the output? I have C multiplied by the state. This state is, again, the previous state multiplied by A and the inputs and so on. I don't know the state, right? This is unobservable to me. I don't know the state, I don't know the system, but I can see the inputs. So how does the output relate to all these inputs? If you open the recursion, you will get this kind of equation that I wrote here. Is this okay? What is the issue with this formulation? The issue is that this is a non-convex problem in terms of the system matrices A and the B and C, because A here appears in higher and higher powers and go all the way to the end of the time. And this is a hard optimization, try to figure out what the A is. Yeah? Okay. There are results in this area. Sometimes gradient descent works, even for non-convex optimization. But in general, this is a hard problem. So what can we do? Well, here is a simple trick we can do. This is called convex relaxation. And we can, for example, try to learn a more general structure than the one that was actually used to generate the sequence. So maybe instead of this polynomial series in A, I'm going to say, okay, I'm going to forget these constraints, relax the constraints, right? It's standard in convex relaxation. So this is the cubic function of A. Okay, forget it. I'm just going to call it M3 and learn a matrix M3 mapping the third input from the past to the future. Yeah, everyone with me? I can do this, right? Now I can just regress. I can regress on these matrices. It's a convex parameterization, and I can try to learn the mapping. But that's not what I'm here to tell you. I mean, this is kind of naive. But how would I analyze it if I were to do this trick? Well, this goes up all the way to the first token that I have seen. And I would like actually to remember the first token. It's important in language that I remember things that happened long ago. Nevertheless, we can't learn as many parameters as there are that we're trying to predict. It's too much. So we have to make some kind of assumption. Here is a standard assumption. If the A matrix is bounded by 1 minus delta, it's strictly less than 1, then this kind of geometric series decreases geometrically fast. And if it's less than 1 minus delta, it's going to be, I need like roughly 1 over delta parameters to learn the whole mapping accurately. Now you can ask, what if it's bigger than 1? Well, if it's bigger than 1, then the output explodes, and this geometric series just becomes larger and larger. It's not stable. So less than or equal to 1 is kind of necessary. And I made the assumption it's strictly less than 1 in order to get some kind of analysis here for this prediction problem. Question? So I'm showing you under some natural assumption, I can learn a linear dynamical system in an efficient way by convex optimization, but there will be some dependence, some polynomial dependence on the condition number of the matrix A of how fast it decays. The past decays in terms of how it influences the future. That's what's happening here. Yes?
I guess when you relax, you should like do something in terms of sample complexity. So if we're not relaxed, yet live with the non-convex problem, you have got a better sample complexity.
Good question. There is actually an open if you have equal to 1, if the system matrix is equal to 1, then it's not identifiable even from a statistical perspective.
Okay.
So it's not only a computational issue, there is actually a statistical issue.
Okay.
Yeah.
And you have to get a 1 over delta.
In using this method you do,
Yeah.
I will show you something a bit different. Yeah. Any other questions from the students, not only professors? Yeah, you're all with me? You know what I'm talking about? Okay. Good. So here's a question. Can we improve the memory performance of this methodology? So I would like to learn a mapping from the past to the future, even if the memory becomes arbitrarily large. Mathematically, this means that the delta goes to 0. The condition number does become closer to 1, and I have this matrix doesn't decay at all. The first token that I've seen still affects what happens many, many iterations from now. Yeah, this is mathematically what it means, delta going to 1. So can we do that? And of course, I want to do it efficiently. So this is a mathematical result in control that I'm going to base the architecture on. It's called spectral filtering. The answer is yes, at least for some special cases. So even though system identification, identifying the matrices A and B and C, that's going to be statistically hard, computationally hard, everything hard about it. I can still do it by moving outside of my prediction set. Okay, so some kind of convex relaxation or improper learning, if you will. And the theorem says that there is an efficient predictor that I can compute efficiently, such that for any linear dynamical system, I'm now assuming the matrix A is symmetric. That's a significant restriction, which I'll discuss in a minute. But under this assumption, even if the eigenvalues of it or spectral radius is equal to 1, I can still have an efficient representation in the sense that I can have some machine with parameter k this machine can represent the output of a linear dynamical system to very good approximation, up to e to the minus k roughly. There is not going to be any dependence here on the spectral condition number of the matrix A, and neither on the hidden dimensionality of the system. The dimension can be very large. It could be infinite dimensional A, and still this is going to be true. Okay, so this is a theorem. I want to explain why it is true and how I can use it to design a neural architecture. But any question, first of all, about what it says? Oops. I'm going the Zoom questions. I'm going to delay until the end if you guys don't mind. You guys have a preference for questions. Okay, I'll take your questions. The Zoom I'm going to delay, but hopefully I will answer them in the end. Any questions here from the audience? Okay, so let me go over. Question?
I have a quick,
Yeah.
what do you pay for the K? Like it says for any K.
The
Better with K.
Yeah, the computational complexity will grow linearly with K. I will show that. So very mildly. And K is going to be like 20. Then we have e to the minus 20 is nothing. Yeah. More questions from you guys that are privileged? You can ask me in person, anything you want. No? Okay, so here is the intuition for the scalar case. I'm not going to talk about, to illustrate the full matrix version of this theorem, just scalars. What happens for scalars? Well, I know that the linear dynamical system, up to the constants B and C, maps the past inputs U according to this transformation. I have 1 times U and then A times UT minus 1, A squared, UT minus 2, and so on. I have this polynomial series. This was the hard thing to learn because it's a non-convex polynomial in general. So rewriting it, I have a vector which is powers of A up to L. L, let's say, is the history length. I'm not limiting it to this point, multiplied by all the past inputs. Let me call the vector of 1A, A squared powers of A, like a van der Waals kind of vector. I'm going to call it mu of A. It lives in R to the L. And I'm interested in learning the system. System means I want to identify what this mu A is. What is this A? It's an L-dimensional object, but the intuition is that it actually spans a much lower dimensional subspace as opposed to R to the L. So even though if I take all such vectors mu A, for all A from 0 to 1, this is going to be full rank. It spans all of RLs. These vectors are linearly independent. Nevertheless, they are approximately in a lower dimensional subspace. So it's a linear algebraic theorem that I'm going to prove in approximation. So the theorem says there exists phi1 to phi k vectors such that for every A 0 to 1, every such system, I can represent as a linear combination of these vectors. And this is an approximation tilde. I have plus e to the minus k here. So plus minus e to the minus k. That's how the approximation decays as a function of k. Okay? So very quickly it becomes extremely accurate with very few coefficients. Yes.
It's quite big, so maybe that's not.
Norm of a being less than 1. No, a can be equal to 1. This is still a valid representation.
Right, but you want a normal big, that's not 1 minus delta.
I don't. I'm now not assuming that anymore. If I were assuming that, then I didn't need to go through this. So I now want to go to delta, even if it's 0, this is still going to be a truth theorem. Okay? Let me now explain what this new basis representation is. And this basis is given by phi1 to phi k. They are the top eigenvectors of the following matrix. I am integrating over all A's from 0 to 1 of mu A transpose. So this is the matrix Z. Integrated from 0 to 1, I get this matrix here. And the top k eigenvectors satisfy this approximation theorem that I wrote here. Okay. Why is this true? And the reason for it actually is very elegant. It's a very beautiful theorem. In approximation theory, this matrix is fixed. I can just write down what it is. It's called the Hilbert matrix. I integrated from 0 to 1. These numbers, they're just numbers, 1, 1/2, and so on. So this is a Hilbert matrix. It's also a Hankel matrix, meaning all the off diagonals are the same. And what Beckerman and Townsend proved in 2016 is that this matrix has an exponential decay of the eigenvalues. Okay, so this is the log scale of the eigenvalues, and this is how I plot them. It looks linearly decaying. This means if I chop it off at some point over here, it's negligible. Everything lower than that is e to the minus 20. And therefore, I can just do a basis shift. That's the entire proof. Okay, it's not a complicated proof. So given my inner product space of mu A and the past inputs, I can do a basis transform by adding the summation phi I transpose. This is an orthogonal matrix. And these coefficients here decay exponentially fast, right? These phi's, by the way, the eigenvectors are fixed. They don't depend on the data. I can compute this matrix Z ahead of time, and I can compute the eigenvectors of it ahead of time. And all I need to do at test time is take the inner product between them and the past inputs and learn these coefficients here, which of course I don't know. This depends on the actual system. This I don't know. This I need to learn. But there are only like 20 numbers here, okay? So I reduce the problem from learning something which is complicated and non-convex to learning a very few numbers, and how many few depends on the approximation I want to obtain, and it depends very well on the approximation I want to obtain. It decreases exponentially fast. Any questions so far? Yeah, it's clear what I want to do. So I moved from a representation, the naive representation from the system that's not convex. I can do a convex representation. That's efficient, but again, doesn't capture memory very well. And this representation, a different basis, this basis happens to be, because of the structure of linear dynamical systems, has a very nice basis representation that allows me to represent any system very efficiently using very few coefficients. These coefficients don't multiply the input, right? They no longer multiply the input. They multiply a transformation of the input according to this fixed filter. Yes. Yeah.
Does your cutoff point where you're allowed to do that approximation?
Good question. So the cutoff point can be anything I want. So it's parameterized by k. For any k that I chop it off, I know that my approximation is going to be e to the minus k, and it does not depend on the system. So for any, so far I only showed it for a scalar system. For a scalar system, the theorem says for any a from 0 to 1, I have an equal approximation up to e to the minus k. That's a good question.
Very chaotic system. You're counting chaotic.
Well, it's a linear system. So linear cannot be, it's a very limited type of system, linear, even though that's pretty much all we can say things about. So it's a linear system. For this linear system, it does not depend on the delta, on the condition number, or on the memory of the system. This is the main thing here. There is no dependence on the delta, okay? Yeah, good question. Other questions here? Okay. So let's reinterpret this approximation result as filtering. What I've showed you is that I can write any output that came from a linear dynamical system as a sum of coefficients multiplied by this inner product here. This inner product are the past inputs multiplied by these special vectors. The special vectors, they don't depend on the data, they don't depend on the system, don't depend on anything. I can just, this fixed matrix, 1, 1/2, 1/2, 1/3, right, this kind of fixed matrix, I can pre-compute it, I can extract the eigenvalues of it ahead of time and save them in my memory, and now use them to convolve it with the past inputs and learn coefficients over these convolutions. Okay. And if you're curious, this is how they look like. So these are some random subset of the eigenvalues of the matrix.
A little bit like a representative theorem, huh?
Yeah, For the special case of linear dynamical systems, that's right. Yeah.
What is the horizontal axis?
This is just the ordinal coefficient.
Okay.
Yeah, there is no meaning to it, it's just an ordinal coefficient. Yeah. What it will represent at time that I apply this method is how much back in time I go. Okay. Yes.
Is this the best we can do while staying input independent?
That's a great question. Let me repeat. Is this the best we can do while staying input independent? It's kind of the best. I mean, how much better can you hope to be? This is already the case, the approximation, the case like e to the minus k, right? So maybe you can be faster. Okay, it's not going to give you too much in practice. Even if you have something faster, I'm going to take k to be 20. And for all practical purposes, e to the minus 20 is negligible in the error that I'm seeing anyways in whatever system I'm building. So I have like a very small constant of filters that I'm going to apply convolution to. I don't know if there is a more efficient representation of this subspace in terms of linear algebra, but my conjecture would be that no, that it doesn't happen. The other answer I have to you is that the eigendecay is tight. The eigendecay of the Hankel matrix is indeed looks like e to the minus k. It's not any faster than that. You saw it in the plot. It doesn't look super linear or anything like that. Good question. Yes.
Down in the previous slide, the previous graph where you said convergence by negative exponential.
Yes.
We assume that after a certain threshold, instead of breaking up the entire data, you just assume everything to be same. Will it affect the end output?
No, because it's a geometric series, right? So if you sum up from k to infinity, k from 10 to infinity, e to the minus k. That's still e to the minus 10, right? So it doesn't really matter what you do with that mass. It's very negligible. It's geometric decay. I don't think you want to use it because it will just be too expensive to start manipulating the entire data with more and more filters, okay? To your with the hat, so you see that there is really a linear kind of, in the log scale, is really a linear decay. It's not any faster or any slower than that. That is the reality of it.
So the motivation was that you knew of this property, so you used it. It wasn't like what
you're asking how we found it?
basically.
So I was proposing to the students, let's look at the data. Let's look at the actual data and try to identify the spectral properties of it. It turned out it was data independent. So I didn't know this. I mean, we kind of found it out, and I think it's very surprising too. It's a very surprising representation. Okay. And you might think, okay, this basis is similar to the Fourier basis or some other wavelet. No, there is a huge difference here. The difference here is, so the Fourier basis, it's an orthogonal transform, like Christopher knows well, right? So all the eigenvalues are 1. This is an exponentially decaying spectrum, so it's different, right? Maybe I should start walking around this area. I don't get any questions from you guys. Any more questions about it? Okay. So, yeah, well, there is a huge limitation to what I said. The limitation is, first of all, I talked about a scalar. What happens, I told you that I want to go to high dimensions. That's the whole power of dynamical systems. I made this whole spiel about having hidden dimension. Okay, here is the thing. If I have a symmetric matrix, this whole thing generalizes very easily. And the reason is that you can diagonalize the matrix A, and when it's diagonal, I can apply this theorem to every eigenvalue separately and sum them up. And the whole thing is not going to affect the filters or anything. It's just going to affect the magnitude of the coefficients that I'm learning here, these m's. These m's are going to sum up across the dimension. It's going to be a larger factor. But that's it. That's fine. That's not a complicated thing to learn. So that's fantastic. Now, how do I go beyond the symmetry assumption? As you may recall from your, this is mostly grads or undergrad? Grads. Okay. So as you recall from your undergrad linear algebra, the an asymmetric matrix, which are very important for control. They are not diagonalizable over the reals. So they might have complex eigenvalues if we diagonalize them, and maybe some of them are the same, and so all sorts of complications. This doesn't pull through anymore. And in fact, there are lower bounds that show you can't have this theorem for a general system. We have strong lower bounds. What you can do, so here is something simple you can do. What if I want to handle negative eigenvalues? Well, I can just take my input and pretend that I multiply every second number by -1. This will give me -a to the power, right? That's kind of a simple trick I can do. There are various other tricks you can perform. If I know the phase, this is a special case of knowing the phase. Phase is exactly 1, well, at 180 degrees. If I know the phase exactly, I can do more tricks like that. I can try to learn the phase. It becomes much more complicated. And it turns out not very important for the sequence prediction. It's very important for other applications, but not for sequence prediction, to look into the complex eigenvalues. And this was observed by the SSM work that I cited from Chris Ray, Albert Gu, and others that looked into this topic. Okay. Any questions about the linear dynamical systems? I'm going to now move to large language models. So that was the theoretical motivation. And I can prove something about, from this point on, much less provable material and more using this intuition to design an architecture. So what I can do is I can take, here is a spectral transform unit that I can build based upon these filters. I can take my input. I have this K is 20, remember? I convolve my input with it and learn parameters to project back onto my output space. So this is something I can do, and I know it's powerful. It's at least as powerful as the best linear dynamical system. If my signal is linear dynamical system, I will be able to learn it pretty well. Here is a simple synthetic experiment that we conducted. We took a linear dynamical system that is almost marginally stable. It has eigenvalues very, very close to 1, and attempted to learn it with the spectral filtering unit and also with LRU. That's an architecture state space model from Google. It comes from Google and is based on a recurrent neural net. And as you can see, convexity really manifests here. You really can see both in the landscape pictures and in the plot that it can learn much, much faster in terms of number of samples. And furthermore, this method is very robust. So it's not sensitive to hyperparameters, whereas if you train an RNN, it is extremely sensitive to all these hyperparameters. And I don't know if you guys use Mamba to feed it to your data and so on. It's very sensitive to the hyperparameters. Okay. So I now want to talk about the neural architecture that is motivated by this spectral filtering. And what we can do is exactly what I showed before. We can build a unit that takes my input, maybe lifts it to a higher dimension, that always for more representation power, then apply spectral filtering, learn the projection, project back, maybe apply nonlinearity or MLP. And I can take this block and put it inside of an architecture, interleave it with SWA's sliding window attention, some kind of small, not as big of an attention as transformer, because that doesn't scale. As I said in the very beginning, it scales quadratically in training and linearly in test time in inference. So I can do a smaller attention, maybe, just to give me some of the capabilities. This is called the hybrid model. And this turns out to be an architecture we use. It's open. You can download it from the website that I gave as advertisement to the talk and try it out. We trained it, I should say Windsor and Isabel and the other undergrads trained it on this kind of model. It's a 2.6 billion model, which is not small. This is 10 billion tokens. It's not, usually you want 100 billion for this data set, for this model size, but will look the same. And this is in comparison to, for example, an attention model. If I just had an attention model transformer and no other modification, you'll see that I get a better perplexity in training. And this manifests also, I cannot show you the plots, but it manifests in evaluation benchmarks as well. This is also, it's even, so I'm not plotting here Mamba 2. This is by my colleague Tri Dao, also at Princeton. He's an expert on these SSMs. And the Mamba does roughly the same as the purple line, a bit better or worse, depending on the setting. Any questions? Yeah.
So I was wondering where this method stands in the general state space modeling and Mamba literature, Because I remember in Mamba, the main two advancements were the dependency,
Right,
the ability to do the parallel scans of parallels.
right.
So do we have any such problems here?
Yeah, so here is a comparison to Mamba also. This Mamba 2. Mamba 2 is one of the later versions. This is not over language data, this is over robotics data. So what we did is we took Mujoko. You know Mujoko? It's kind of a framework for robots to control them. We took a policy, some pre-trained policy, measured the robot movements, and try to predict them. It's also a sequence prediction problem. It's much lower scale, so it's easier to experiment with, and this compares Spectral transform to Mamba 2 in transformer, and it does better in this particular experiment. We kind of across the board see doing competitively. I should say, so for language, transformer is state-of-the-art, considered to be state-of-the-art. It's better than Mamba and hybrid and all these other things. The reason it's better, it handles memory better. That is the common thought in large language models. Whereas this stand, I believe it can scale up, but I can't tell you definitely because I don't have results for very large models that I can share.
So the scalability is not because of those Mamba tricks, but because of using the small, like the small bases.
Well, you're asking why, why can I scale to longer memory? Yes, the theoretical motivation is that I can handle delta even 0, right? So delta even 0, so Mamba is a state-space model, it can only handle some constant delta. But this can handle delta equals 0, and we see it. We see it in experiments. I'll show you experiments that you can actually see how well it generalizes to long context. Yes?
So this data is trained on audio.
This is not audio, this is robotics data, movement data. Yeah, movement.
What is the token here?
A token is a position. Let's say, so you measure the robot is walking like this. Then let's say you measure where I'm holding the stick. This is a 3D coordinate in space. That's what I'm trying to predict. Okay? Yeah. Audio data would be cool. If you do try it out, let me know. Okay, so there are all sorts of sequence data that I think should be tried. And maybe some architectures are better or worse for various modalities. Okay. So I talked about linear dynamical systems, why spectral filtering is interesting in this context, and about the neural architecture that arises. I will now want to talk about algorithmics. So how can we use this to efficient generation and provable length generalization? And let me start with inference. So inference, what do we do at inference time? This is the model which I described is called the convolutional model, which means that it generates the next token by taking inner products with a bunch of filters and then projecting them, right? That's what I showed you. So for illustration, I have only a single filter here, this kind of wiggly thing. What do I need to do for creating the next token? Well, I need to inner product this filter with my past inputs and multiply by some learned parameter. Now, transformers naively, they need to compute the inner product with all the past. That scales horribly with the past. RNNs, state space models, constant, independent, it's very efficient. But naively, if I were to apply, I also need to take inner product with the entire past, and that's slow, right? That will take me also, same as transformer, not any faster. So kind of beats the purpose of what I wanted to do in terms of speed. But the good news is, we can actually bring it down to some polylogarithmic in the past, which is very efficient. This is already almost as good as a constant. So how can we do that? And the idea is that we can use the fast Fourier transform to compute convolutions very fast. So we know that convolution in time domain is product in spectral domain, right? And we call this trick future fill. The idea is that this filter that I'm inner producting with the past inputs, what will happen the next time I want to predict a token? I need to shift it by 1, and then shift it by 1, and shift it by 1. Now, it's not exactly, once I shift it, there will be another thing added, right? And I shift it by 2, there are 2 things added, and so on. But I could have kind of pre-computed by convolution of this filter with the past inputs a bunch of future information that I can now reuse. So I'm going to do the FFT, which computes L inner product at this time L log L instead of L squared naively. And that will give me information to kind of the future inner products here. And then I'm going to fill in the missing information. This is kind of one naive thing I can do. Maybe not naive, but not very hard. Let's reason about the complexity of this algorithm. Is the algorithm clear? Yeah? Okay. So I'm pre-computing all the inner products by convolutions, right? FFT. So every once in a while, let's say every k iterations, I pay log L, that's the FFT. Now what happens? Okay, first time I pay 1, then 2, then 3, then 4, right? So I go all the way up to k, and then I do the FFT again. So the cost is going to be something like summation of 1, 2, 3, 4 up to k, plus L log L divided by k. That's the amortized price per token. Yeah? And you can optimize it. You can take k to be, for example, root L. That will give you root L complexity amortized per token. Yeah? Chris, this is okay for you for sure, okay. So this is one thing, and here, what am I doing? I'm taking advantage of the fast Fourier transform, which is a well-known implemented algorithm, to speed up this particular convolution that we have. It will actually apply to any filter. I'm not taking any special advantage of the filters that I showed you. It will work for any convolutional model. So this idea can be applied recursively. I'm not going to go into details here, but you can break it up into smaller pieces, apply the future field in each smaller piece, and so on. And this will give you theoretical improvement of something like log L. So that already matches what SSM will do. This is an experiment for running time, generation. So what generation or inference are the same thing for the transformer versus naive convolution. This is just, it looks a bit better. It's the same. It scales up quadratically in terms of running time. And this is the future field. This is over a 2-layer neural network and tokens, language tokens. So this is very, very important, at least when you want to serve your model. Final point, length generalization. What does length generalization mean? This is a very important concept when you're dealing with large language models. Those of you who have, I can see some people nodding. If you train the large language models, you know what I'm talking about. What you want to happen is you want to train over your training data. You have all these questions answering. Oh, can you please explain to me why the transformer is quadratic time? Just like I showed in the very beginning. Gives this long list of text, right? What if now I give it a story? Here's Lord of the Rings. Please tell me what Sauron did in chapter 1. He needs to remember all the way. It's a much longer context than what it used to in your training data, right? How do we know that our model will be able to generalize to a context length longer than what we gave it to train with? Yeah? How do we know that? So in my opinion, this is an understudied question. I was just talking in the morning to some colleagues here, and the gap from theory to practice is only increasing. This is an example. It's a good example of where we increase the gap. We don't have any theory for saying what to do with this. So here is a new result, which talks about length generalization, and we try to formalize what it means. And one of the concepts that we come up with, we call asymmetric regret. It's not a probabilistic notion. I like to deal with game theoretic worst case notions. It's just, I'm used to it from my background. So we compare the prediction of our algorithm with a certain context length, let's say L prime, to a predictor that has much longer context length. Maybe it can see much more. If we can get sublinear regret guarantees for this problem, just like I showed it how to do in the first part of the talk, for linear dynamical systems, right? We had some regret bounds, some convergence. If I can do this, this is a more challenging task because I'm comparing to a more powerful entity than what I myself am doing. So I myself am looking at some L prime. I want to compare to some L, much bigger than L prime. And if I can get a non-trivial guarantee here, my claim is that this will give me a meaningful theoretical result for length generalization. Yeah, so intuitively clear what I'm want to say? Okay. Now here is a property. I can only say this, I don't know what to say to prove the length generalization for transformers or for other machines. but I can say something about the particular machine that I talked about. And that comes from the fact that it has a special structure. So the machine I'm talking about has spectral filters that come from a very precise mathematical object, right? They have these eigenvalues that come from the linear dynamical systems. For this type of machine, I am able to say something, and the reason is the following. I can take my filters of length L squared and note that it is actually can be written as a outer product of two smaller filters, one with the parameter alpha and one with the parameter alpha to the L. It's just a fact, mathematical fact, because what is this long vector? I have one alpha squared, da, 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 da. At some point, I can chop it off and say, oh, the rest is alpha to the L times alpha squared, alpha cubed, right? So on. It has a structure. Nothing very deep about the structure, but it's a nice tensor structure that we can try to exploit. This fact means that I can try to learn, instead of the original filters, I can try to learn these outer products of them. And I have some kind of containment. So this set of vectors, u alpha to the size L squared, is contained by all outer products, even if I don't restrict them to be alpha and alpha to the L. I allow this to be alpha and beta, some other beta. It doesn't have to be alpha to the L. There is a strict containment here. This fact already suggests some intuition for why we would have length generalization. And the intuition is, what if I learn the coefficients up to root L, roughly 10 root L or something like that? Then I saw some of the alpha, I saw some of the beta. Potentially, I should be able to reconstruct it all the way to much longer lengths than I actually saw. Okay, that's the intuition. It can be made precise, and what we can prove is that we can have square root regret versus with only square root observation versus a method that sees the entire history, so T. So we can kind of reduce the observation by square root and still maintain non-trivial regret bounds. And we can see it actually very clearly in experimentation. So what we have here is a copy task. This is one type of tests that people conduct for large language models. The idea is, why don't you copy this token that appears after this black picture and put it all the way to the back. So this requires memory. And learning with these tensor filters achieves much, much better generalization than the naive filters that I described. Okay. So this is only, I think, the tip of the iceberg. There is so much to discover that has to do with the structure of linear dynamical systems and potentially enhance it to other non-linear dynamical systems. The whole concept of length generalization is very understudied. I only show it for a very particular type of signal and type of machine. Can we do something much more general? So just to give you two recent advancements, one on generation and one on length generalization. Any questions about these two things? Yeah.
Spectral transformer looks similar to the rotary positional embedding based LLM. So is there any comparison between these two? Or
Okay, good. The question, let me repeat the question in case people didn't hear. There is something called rotational or positional embedding, more generally, right? Rotation is one type. So positional embedding in large language models, this is done so that the model will remember how far away. So you basically add to each token some kind of number, usually a sine or a cosine. So you multiply your inputs by that sinus. And the point is that the algorithm kind of knows how far away in the back it was and be able to use that information. These techniques do not use positional embedding at all. So the filter already has some built-in, because of this sign and decay, it has some that's the conjecture, I don't know how to prove it. It has some built-in property like that, and we don't actually need positional embedding for both the theory or the applied results that I showed you. Okay, so let me summarize. I talked about sequence-to-sequence prediction. The novel method here is that we use fixed filters. We don't try to learn any filters. They come from a theory of linear dynamics, which is related, but is not, that's maybe the best model we have for some hidden Markov models and so on, but it's not language, obviously. So nevertheless, this theory does give rise to these fixed filters, It can provably learn symmetric marginally stable linear dynamical systems, which we don't know how to do by any other means. And we can design a neural architecture based upon it, which is based on convex optimization at the heart of it, right? I'm just doing regression. That's all I'm doing. Filtering and regressing over the inputs. I talked a little bit about fast generation and about provable length generalization. And if you want to learn more, we have this book online, which is about control, but nevertheless contains a lot of the material here about both linear dynamics and spectral filtering. Doesn't contain any neural nets, but contains the theoretical background. If you want to know about deep neural nets and sequence prediction, we have a webpage that I think I posted to the talk announcement. So you can go to there. And I'd like to thank you very much for your attention and take questions if you have. I'm okay now with the Zoom too. If the Zoom people want to ask, I'm fine with that too. But yeah. Yeah.
What would change you instead of when you first motivated everything? You started from the regret arguments and the online control. If instead we had the more classical optimal control arguments.
Oh, okay. That's a good question. So optimal control is maybe the most well-studied paradigm for control of dynamical systems, and it doesn't assume, it's not based on adversarial noise, it's based on stochastic noise and norm dynamics. The advantage in optimal control is that you can do system identification many times. You have stochastic noise under some assumptions, but still for marginally stable systems, we don't even know how to do system identification. System identification means that you can identify the matrix. It's not even well defined. If you have a marginally stable system, all diagonals are one. Up to rotation, they're all kind of the same. So the whole thing is not well defined and you cannot identify it. So you can have multiple eigenvalues of the same. So that technique, I don't see how it will work. The reason why we're able to overcome it is because I'm not identifying the system at all. I'm learning some other creature, and that is well defined. That doesn't have all the issues that system identification does. And it so happens the regret framework is important in the sense that you can compare apples to oranges. You're not trying to learn in the same domain that the data was generated from. It was generated by an LDS, great. I'm now learning something else, which is more powerful than that. And because I'm learning something more powerful, I don't lose anything in terms of expressivity, but I don't get the computational issues that I would get with the original system identification. Okay? Good question. Do I have to look at the Zoom myself, or you guys have some kind of method? I don't know if there is. If someone is at the Zoom and hears me, I'm happy to answer, but you had to. I don't see anything.
Can I ask a follow-up question on your?
Yeah, please.
So
Yeah.
I guess, the notion of regret error makes sense because what you're saying, it's not identifiable, so you just want to be competitive with prediction.
That's right.
Although you guys are making an even stronger assumption than I guess classical dynamical systems where you're not actually controlling these anyway. It's right? It's arbitrary. Like you're not assuming. I guess you could assume that the data is generated by a true linear dynamical system,
right?
Marginally stable.
Right. It's a bit more subtle. You touch upon a good point, and it's a bit more subtle. I didn't go into it on purpose. What I'm showing is that the data. I'm not assuming anything but the data. The data can come from a nonlinear something mumbo jumbo, not corresponding to any dynamics. I'm only competing. I'm competing with some class of predictor. That predictor can be really bad. But nevertheless, if that predictor came from a linear dynamical system, if the data is linear dynamical system, the predictor is going to be good. I'm going to compete with it, and my result is going to be meaningful. So just like any regret, if the best predictor in class is no good, my result is not going to give me a good result. I'm also going to do poorly, right? So in that sense, I'm not assuming anything about the noise. It could be adversarial. It could be the whole signal could be mismatched. Yeah, that's right. Okay, yeah, I can. You want to see that?
Yeah. So,
I think that's over here, I think.
Yeah, exactly. Then, okay, so let me read the questions from here.
Yeah.
So the question first, for learning dynamical systems, at least from the control theory literature, it is actually easier to learn marginally stable systems precisely because the signals don't delay fast.
Yeah, I disagree to that, and I don't know how to do it.
Don't decay
fast.
fast. I mean.
Yeah,
And then,
I disagree. Yeah.
Okay.
Yeah.
There was a question about the lower bound. I don't know if it was regarding maybe the regret bound that you showed before, or
Lower
Or-
bounds.
the lower bound. Yeah.
Okay, so there is a lower bound for learning an asymmetric linear dynamical system, which depends on the number of the dimensionality. I don't have a board here. Oh, I do have a small board, but I can
Yeah.
construct. You have like a pen?
Well, we typically.
Okay. Would-
Yeah.
Okay, I can describe the following. Here is a dynamical system which I can make to be linear. Take 5 tokens ago what I said, and that's going to be the next token. This is a linear dynamical system. It's asymmetric. I can have a matrix. You just kind of, it's like a rotation matrix. You take the one from 5 ago, put it on the way to the top. The rest are like off diagonal. You can see this requires memory of 5. There's absolutely no way I can do it without the memory of 5. And the asymmetry here is crucial. So this can blow up to arbitrary dimension. That's the lower bound, basically. And that's a limitation of the technique. It doesn't seem to manifest in practice. I don't know why, but it doesn't seem to manifest. And we're not the only ones to discover that. So I should give credit to Chris Ray Group, Hippo, Albert.Gu, and so on, that also observe that the dominant eigenvalues are all real in sequence prediction.
And the last comment here is there are many post-training things done on LMMs, such as RL, HF, and IFT. Is this shown to be possible on linear state space? Do you think this would work?
Yeah, we're actually experimenting. So the question is about fine-tuning. Fine-tuning, most research in academia in large language models deals with fine-tuning. And the reason is it's just too hard to do pre-training. We don't have the resources in academia to train on these very large corpuses and large models. Indeed, we're investigating the use of this architecture for fine-tuning. I hope others will investigate it too. It seems to be promising, but I don't have any results right now to share with you. Yeah.
Okay.
All righty. Thank you very much.
A small gift for you all to
Oh, wow.
remember about us and
Wow, this is great.
the photo. So
This is great. Thank you so much. Yeah, this is fantastic.
Mary, maybe in the center.
Oh, we do a photo? Okay,
Yeah,
cool.
close to the photo.
Okay, good. Let's do it.
Got a bunch, they should be good.
Perfect.
Oh,
Thank
did
you
you
so
send me
much.
one?
Yes,
Why
absolutely.
don't you check, make sure it's okay?
Yeah, I'm sure it's fine.
Let's just check anyway.
Oh, this is great. Thank you so much. Oh, wonderful. Thank you. Thank you so much.
I'm gonna take it to the office so that I don't have to walk around.
I love it.
Yeah, we always keep,
Wow, this is fantastic. Thank you so much. Yeah.
So we're gonna go for lunch now. We're gonna go to my office first so that we can grab the.
Get our
agenda.
photos.
Sounds good. Yeah.
Great stuff. Thank you so much.
Oh, thank you. Pleasure. Yeah. Yeah, it was good for the audience. I didn't know if,
Yeah,
yeah.
yeah.
Okay.
Yeah, I think it's good, yeah.
Yeah, okay, good. Good.
Chris, you will have the student that was asking you a lot of questions, so you will have, because you used to the control.